Good afternoon, sir.
Yeah, good afternoon. Um, okay, so we'll discuss microscope and telescope. Now, before we discuss all this, we need to know about what is near point and far point for the eye. Do you know the meaning of near point and far point?
Yeah, like,
Near point is basically the closest distance that you can place an object near the eye and you can still see it clearly, right?
yeah,
That is called least distance for distinct vision. So that is usually 25 centimeter, correct?
yeah,
And then this far point is basically the farthest thing that you can see. So that can be taken as infinity because you can see the stars and all, right?
yeah,
So this near point and far point stuff will be important because whenever we discuss all of these instruments, uh, you can operate the instrument in multiple ways. Like you can operate it in such a way that you form an image at either near point or far point, right?
yeah,
Like the image can be at infinity and you can still see it, or image can be very close to the near point and then you can see it. And in both the cases, the magnification and all will be different. Magnification is obviously different. It's the same instrument, but if you operate it in a particular way, your magnification will be different. And if you operate it in a different way, your magnification is different, right?
yeah,
The idea about magnification that you should get a sense of is mostly, let's say this is the eye and this is an object h and at a distance, let's say x1, and another object or another situation where I is here and h is here and this distance is x2, right?
yeah,
The same object, it's just that the distance is different. Now, how do we get the sense of magnification here? Magnification is measured by the angle that it makes here. This is angular size. This angle theta 1 is your angular size of this object, right?
yeah,
And this angle theta 2 is your angular size here. So technically, you can say that you are thinking of it like a circular object and you're trying to measure the arc length here, right?
yeah,
That denotes the size of the object when you see it from here. So because in circles you have L is equal to R theta, you can say that H is equal to x1 into theta, for theta 1. So theta 1 becomes H by x1, right?
yeah,
And similarly here theta 2 becomes H by x2. So
yeah,
greater the theta, the greater the theta, the greater the size of the object that you will see, greater the size of the object appears to you, right?
yeah,
In general, what you will do is later when we look at particular instruments, what has to happen is in one case you will measure without the instrument what was the size of the object, and then with the instrument what was the size of the object, right? And all the time we are talking about angular size, right?
yeah,
This notion that what is the angle made by the object at the eye, and that denotes its size. So once you have the two angular sizes without the instrument and with the instrument, then you can compare that to get the magnification. The ratio of those two sizes would be your magnification, right?
yeah,
Okay, so with all this, now we can start talking about what is a simple microscope, compound microscope, then telescope and all. So simple microscope is basically just a convex lens of small focal length. Convex lens of small focal length. And what does it do? So we can draw a few diagrams. You can say like this is the eye, and let's say we have an object here, H, at a distance D. What is a distance D? D is the near point, right?
Yeah.
So we are trying to observe a small thing. We have brought our eye close to it so that we can see as big an angle as possible, right?
Yeah.
So this is without the instrument. So this is your theta naught. So angular size without the instrument, theta naught is h by d, right?
Yeah.
H by d, basically d is the near point distance, right?
Yeah.
Now, if you put a convex lens, you can put the convex lens like this. The object is between the focus and the optical center of the lens, and your eye is this side. So focus is somewhere here for the convex lens. So then what will happen is virtual image will be formed because it will be like this. I mean, that is a dotted line actually. The actual rays will go this way,
Yeah.
and one set of rays will pass through the optical center, and actual rays will go. They have drawn it slightly wrong. It should be diverging like this and like this, right?
Yeah.
And when you reproduce it back here, you get a larger than the object sort of image here, right?
Yeah.
Correct. Now, you can ensure that your object is placed at such a distance u so that this distance turns out to be d, right?
Yeah.
Like this u can be selected by you, right?
Yeah.
So that the image is at a distance d, so that from this side you can see it because it is at least distance of distribution, right?
Yeah.
Now in this case, the angle that matters is this angle, right?
Yeah.
This angle matters because this is the image height now, h dash and d, right?
Yeah.
So this angle will become also the actual height also matters. So if you see actual height, this angle, h by u, right?
Yeah.
Actually, this is the same angle as that. So you can say theta is equal to h by u, right? It's the same angle because same line is being reproduced here, right?
Yeah.
Theta is h by u, and u you can solve because we have convex lens formula 1 by v minus 1 by u is equal to 1 by f. And here u is negative, v is negative, f is positive, right?
Yeah.
1 by v is equal to 1 by f plus 1 by u, and u is, oh, we have to find u. So we know the value of d, right?
Yeah.
So we know d is minus, v is minus d, right?
Yeah.
Minus 1 by u is equal to 1 by f. Therefore, 1 by u is equal to 1 by minus d minus 1 by f, right? Correct.
Yeah.
Correct. So it becomes fd by f plus d negative, right?
Yeah.
U will come out to be this, right?
Yeah.
It will be negative. That means that it is on this side, right?
Yeah.
So the theta angle now you can write down. Theta angle becomes h by fd f plus d, right?
Yeah.
So this is your theta angle now. This is the angle that the angular size of the image now, right?
Yeah.
So in this case, when this is the case where you're operating the simple microscopes to in such a way that image is at near point, right?
Yeah.
Image is at near point means your eye is actually quite strained to look at it, because when you look at things close, you have to strain your eyes, right? All the muscles are contracted then. It's not in a relaxed state, right?
Yeah.
In that situation, this is the image size, and the magnification in this case becomes mn, let's say, is equal to image size right now, which is hd plus f by fd divided by without it, right?
Yeah.
H by d. Without anything, this would have been the image size, right?
Yeah.
So this becomes HH cancels, TD cancels, you get 1 plus D by, right?
Yeah.
So this is the magnification due to simple microscope when the object is making an image at the near point, right?
Yeah.
Makes sense.
Yeah.
You can also do the same experiment. You should write this down, how we have calculated all of this, right?
Yeah.
You have written this.
Yeah. I've written it down.
Okay, so you could have done the same experiment in a slightly different way, where you would have placed the object at the focus, right? If you
Yeah.
place the object at the focus, then the image would be at infinity behind, right?
Yeah.
That would be the far point image. Like this is the object at the focus. So you have something like this, and you have rays that go like this, another set of rays that go like this. These are parallel, so your image will be behind at infinity, right?
Yeah.
So if now your eye is here, you will see the image at infinity very far away, right?
Yeah.
Again, the angle that the image makes will be still this angle, but in this case, this angle theta is equal to h by f, right?
Yeah.
Theta 1, right?
Yeah.
And original was h by d, right?
Yeah.
So therefore, magnification in that case would be h by f divided by h by d, or simply d by f, right?
Yeah.
So this is the magnification when you are looking at it in a relaxed state. Far point, the image is at the infinity far point, right?
Yeah.
So notice that the magnification when it is at far point is lesser than the magnification when you see it at the near point, right?
Yeah.
Magnification here is 1 plus d by f, right?
Yeah.
So that is your simple microscope, which is in two ways you can operate it, so that you can see it at far point and near point, and you get two different types of magnifications, right?
Yeah.
Now compound microscope. Compound microscope, you basically want to increase the magnification and make it bigger than d by f or 1 plus d by f. So here there are actually two lenses are going to be used here, right? One is called the objective and one is called the eyepiece, right?
Yeah.
And they are on a common principal axis. Okay.
Yeah.
Uh, so I'll draw the figure. Let's say this is the eyepiece and this is the objective, and this, let's label it uh, object is placed at a distance u, which is slightly greater than the focal length of the objective. So if the focal length is here, focus is here for the objective, object is placed at a distance u, which is greater than this focal length. right?
Yeah.
Now, if object is placed in such a way, then this object is, let's say, AB, and it is a convex lens. If the object is beyond the focus, the image will be between C and F, right?
Yeah.
On the other side, right?
Yeah.
So somewhere between F and C, somewhere here, you would get an inverted image. It's a real image, right?
Yeah.
A dash, B dash, right?
Yeah.
Correct. Now, this is at a distance of, let's say, UE from the eyepiece, right? Correct.
Yeah.
And you have to ensure that UE is less than focal length, right?
Yeah.
Why? Because if it is less than focal length, then focal length of eyepiece is somewhere here, then you will get a in magnified image somewhere like this, right? Vertical, virtual magnified image, right?
Yeah.
I'm not drawing the rays because it will just complicate the diagram. Okay.
Yeah.
So, but this is what will happen. You will place first object near just beyond the focal length so that its image will form here in the middle somewhere between C and F, but it will be inverted. And this is a real image. And then this image should fall inside the focal length of this eyepiece, right?
Yeah.
Correct.
Yeah.
Now, again, two ways you can operate it, right? One way is that this distance should turn out to be the D, right? So that you can look at it from this side and it is at your near point, right?
Yeah.
Correct.
Yeah.
And the other way is that maybe you can ensure that A dash B dash falls exactly on the focus and the image is formed at infinity then, right?
Yeah.
So we will analyze the infinity case later. First, let's analyze the near point case. So, okay. So overall magnification of the compound microscope will be product of the magnifications of first and second, right? So first there will be this magnification due to objective, right?
Yeah.
And there will be the second eyepiece's magnification, right?
Yeah.
So, okay. So objectives magnification, magnification in case of objective would be, if you remember, for a focal length, magnification is given by what formula? Minus V by U.
Yeah.
By U. Minus V by U. I don't remember very well.
It's minus V by only.
Minus V by U. Okay.
Yeah.
So then let's put the values. Your V here is uh, okay. Actually, I will use the lens equation to write this. 1 by V minus 1 by U is equal to 1 by F. So I want to find out minus V by U, right? So
Yeah.
this is U by V. U minus V by UV is equal to 1 by F, right?
Yeah.
So, okay. Hmm.
You
Okay,
can multiply by V both sides.
we can multiply by V. So you'll get 1 minus V by U is equal to V by F, right?
Yeah.
And minus V by U is equal to V by F minus 1, right?
Yeah.
So you will get V minus F by F, right?
Yeah.
Uh, That is one way to write it. But I want to write it in terms of U actually. I don't want to write it in terms of V here. So, okay, what we can do is if I multiply by U, I get U by V minus 1 is equal to U by F, right?
Yeah.
So U by F plus 1 is equal to U by V, right?
Yeah.
So U plus F by F is U by V. So V by U will be F by U plus F, right?
Yeah.
So we can say minus of F by U plus F, right?
Yeah.
That is equal to your minus V by U, right?
Yeah.
Now that is in terms of the focal length of this, like let's call it FO, and in terms of the U here, right?
Yeah.
And obviously you will have to put everything with the correct sign here. So you will realize that when you put, because everything in the optics formulas has to be put with correct signs, right?
Yeah.
You will have to put U as negative whatever, right?
Yeah.
Then you'll get the correct value here, right?
Yeah.
And magnification due to the eyepiece. Now eyepiece acts like a simple microscope, right?
Yeah.
And this is the case when we are doing near point vision, right? We are looking at it from the near point, right?
Yeah.
So that will be 1 plus d by f, right?
Yeah.
Overall magnification, capital M, is m naught into me, which will be minus v by u into 1 plus d by f, and you can put the value of f naught by this thing as this thing, right?
Yeah.
For minus v by u, you will have to put the value of this.
Yeah.
Uh, in case the final image is produced at far point, in case this was on the focus, right?
Yeah.
Second magnification me would have been just d by f, right? Fe.
Yeah.
This is fe by the way, right?
Yeah.
And the first magnification would have been same, minus v by u, right?
Yeah.
Correct, no?
Yeah.
And you would have gotten minus v by u is equal to minus f naught by u plus f naught. And you'll multiply these two, and that is the second case when the image is at far point, right? Correct.
Yeah.
So in general, like you need to know the basic setup, like the object is placed beyond this and the image is found here between focus on optical center of eyepiece and so on. And after that, you have to know how to write the magnification from objective and magnification from eyepiece, right?
Yeah.
So it is fairly straightforward only if you understand your basic simple microscope stuff and what is the arrangement here, right?
Yeah.
Then the next thing is, what is the tube length of a compound microscope? So sometimes they use such things in your microscope. So such terms can be there in question. So tube length is basically the distance between the two lenses. Distance between the two lenses, right?
Yeah.
Between two lenses, objective and eyepiece, right? Now, there are two cases in which you can operate the compound microscope. One is the near point vision case, right? Which we just drew, right?
Yeah.
So in the near point vision case, your length, tube length would be V plus UE, right? If you
Yeah.
V was the distance from here, and UE was the distance from here, right?
Yeah.
Okay. Now V can be written as uh, using the equation for this, right? You can solve for V here, right?
Yeah.
1 by V is equal to 1 by U plus 1 by F naught. So V is equal to U F naught by U plus F naught, right?
Yeah.
Again, you will have to put minus sign for U, but positive sign for F naught, right?
Yeah.
Because focal length of a convex lens is positive and U is negative here, right?
Yeah.
Don't put actual values here, then it will be wrong, right?
Yeah.
You have to put with the correct sign. Every time in optics, put the right sign according to the sign convention. So ln is equal to U F naught by U plus F naught plus, now we have to find out UE. And UE, how do we find out? We know that the final image is found at D, right?
Yeah.
In this case. So we'll say 1 by V minus 1 by U is equal to 1 by FE, right? And we need to find out UE. So 1 by V minus 1 by FE is equal to 1 by UE, right?
Yeah.
And V is actually minus D, right?
Yeah.
So 1 by minus D minus 1 by FE is equal to 1 by UE. Minus can be taken out and it is FED by FE plus D negative. That should be your UE, right?
Yeah.
So you will add this to this, right?
Yeah.
And again, put the correct signs for everything. FE is positive and D is now a magnitude because we have already put the sign, right?
Yeah.
You understand?
Yeah.
We already put the sign here. Therefore, D is now just a positive number, right?
Yeah.
So you add these two lengths and you get the answer for total length, right?
Yeah.
And in the case when you are doing far point vision, right?
Yeah.
This UE has to be focal length FE, right?
Yeah.
The V remains unchanged,
Yeah.
correct? So the far point vision length of the tube will be V plus FE, right?
Yeah.
Okay. So that is about your microscope, compound microscope. I don't think anything else is important here. Uh, then we can look at the telescope now. So, okay. So telescopes are several types. We'll first look at the refracting astronomical telescope. Astronomical telescope because you want to look at very far off objects, right?
Yeah.
So generally, if the objects are very far, they will subtend a very small angular size on your eye, right?
Yeah.
They appear very small, and the telescope's job is basically to produce a magnified image of such bodies, right?
Yeah.
And have a larger image size, right?
Yeah.
So now a simple astronomical telescope will again consist of two lenses, objective and eyepiece. The objective is supposed to be a convex lens of long wave focal length, okay, and it will form a real image at focus, right? Real image at focus. Why? Because all the rays will be from infinity separation, right?
Yeah.
Because they are astronomical bodies, so all the image will be found at the focus, right?
Yeah.
For the convex lens, right? This lens, objective, right?
Yeah.
And now let's draw it. So let's say here there is a focus here, and parallel rays came from infinity and they were focused here. So you got some object here, right? Okay. Now, this is your AB object. This image, this image of the heavenly body at infinity acts as the object for the eyepiece, right? And that should form a virtual enlarged image, right?
Yeah.
Correct.
Yeah.
Actually, I should draw it not like this. I should just say that, let's say rays came from here and they got focused like this, right? From infinity. And this was my objects, the star's image. And then you put your objective eyepiece here, right?
Yeah.
Now, again, two cases. You can ensure that this is at the focal length of the eyepiece. And in that case, final image will be at infinity, right?
Yeah.
And you can ensure that this is inside the focal length, but at such a distance that the final image is at D, right?
Yeah.
Again, virtual and enlarged image you want to create, right? All the time, that is what you're trying to do. You are trying to create a virtual and enlarged image for your eyepiece, right?
Yeah.
So either you view it from the far point situation where this distance should be focal length of eyepiece, or you view it in the near point setting, right?
Yeah.
It's the exact same principle actually, right? The only
Yeah.
difference is that this one should have a big focal length so that it can absorb enough rays, and big aperture so that light can come enough and form an image here, right?
Yeah.
Now, again, magnification, if we want to find out, uh, first thing that we need to do is to realize that always the object is considered to be located very far away, right? Correct.
Yeah.
So without a telescope, what was the size of the object, right?
Yeah.
So that you can get a sense of by looking at these rays and what angle it makes, right?
Yeah.
This angle would be your angle with, suppose your eye was here without the telescope and stuff, then this would be the angular size, right?
Yeah.
Correct.
Yeah.
So now first image is produced in the focal plane of the objective here, this AB. And if AB is H, right? Correct.
Yeah.
Then we can say that this distance will always be F naught, right? Correct.
Yeah.
So this angle will be same because this angle is vertically opposite angle here, right?
Yeah.
You get alpha is equal to H by F naught, right?
Yeah.
Because this is coming from infinity and getting focused on focal length, right?
Yeah.
So that is your first relation, that alpha is H by F naught. That gives you angular size of the actual object, right?
Yeah.
Now for angular size of the image, it is a virtual image that is formed like this. Now you have to actually find out this angle, which is same as H by this, right?
Yeah.
H by whatever is this distance, right?
Yeah.
So in two cases, for the far point, you will have beta, which is this angle. Beta will be equal to H by Fe, right?
Yeah.
For the far point case, right?
Yeah.
But for the near point case, you will have to do a little bit of calculation because this distance you will have to find out, right?
Yeah.
You say 1 by V minus 1 by U is equal to 1 by Fe, and you will say, I need to find out this U. So V is 1 by minus D minus 1 by Fe is equal to 1 by U, and Fed by Fe plus D, right, comes as U, right?
Yeah.
Correct.
Yeah.
That becomes your U, and now you will say beta in that case would be H by U, right?
Yeah.
In the near point case, right?
Yeah.
And always your now overall magnification would be what would the size be without a telescope and what would the size be with the telescope, right?
Yeah.
Beta by alpha you have to do. So in the far point case, it is very simple. Beta is H by Fe, alpha is H by Fo. So it will become Fo by Fe, right?
Yeah.
In the far point case, right?
Yeah.
In the near point case, it will become H by U by H by Fo. So Fo by U, right? Fo by Fe D, Fe plus D, something like this, right?
Yeah.
So this is Fo by Fe 1 plus D by F. 1 plus Fe by D, right?
Yeah.
Like you should write it a little clearly, but you understand the logic.
Yeah, I do.
Without the telescope, find the angle. That angle can be estimated by noting the size of the image here at focus, right?
Yeah.
Because it will be like this. Parallel rays will be coming and they will be converging at this focus after refraction, right?
Yeah.
This is H. This angle and this angle are same, and this is equal to Fo, right? So
Yeah.
alpha is always H by Fo. Now for beta, you have two cases where this image was at focus and the final virtual image was at infinity. That is the far point case, right?
Yeah.
And that angle would have been beta would have been H by Fe, right?
Yeah.
And the other case would be when it is not at focus. So it is somewhere here and the image is somewhere here, and this distance is D, right?
Yeah.
So you need to find out again this UE. So your beta is again H by UE, this angle. And UE you can find from lens formula. And if you do the derivations, it comes out to be beta comes out to be H by D Fe Fe plus D, something like this, right?
Yeah.
And magnification in the far point case comes out to be Fo by Fe, and negative sign will be there because it is inverted image. And magnification in the near point case comes out as minus Fo by Fe 1 plus Fe by D, right?
Yeah.
Makes sense, no?
Yeah.
Then similarly, you can talk about tube length of a refracting telescope, right?
Yeah.
In the first case, when the image is at near point, tube length is Fo plus UE, right?
Yeah.
And in the case when image is at far point, tube length is Fo plus Fe, right?
Yeah.
Correct. So
Yeah.
three calculations have to be done, the same derivation, right?
Yeah.
Then you can also have a situation. Okay, hold on 1 second. There's a call. Okay. Then there is a modification, slight modification to the astronomical telescope, where we have a terrestrial telescope, right?
Yeah.
So what is the difference between this? Terrestrial telescope, you can put in a lens between objective and eyepiece. Basically, what you want to do is not have an inverted image, right? Correct.
Yeah.
So in all the telescopes that we have seen so far, the final image is inverted with respect to the initial object, right?
Yeah.
But if you want to look at far off things on Earth and all, you don't want to be opposite inverted images, right?
Yeah.
So what you can do is just do this modification. Your objective and all is same. Like this, everything is same till here. This is an image formed AB, right? And then you can put a lens here. Put a lens here such that rays from it, this is at 2 times f1, okay? So it is at the center of curvature of this lens, right?
Yeah.
So the image will be at the opposite center of curvature, right? And inverted, right?
Yeah.
You understand?
Yeah.
Like if I put an object at C, the image is at the other side C, right? And inverted. It's a real image, right?
Yeah.
And then you have your eyepiece, and then erect image is formed normally, right? So this is a virtual image, correct?
Yeah.
So basically, just by inserting this extra converging lens in the middle, such that this image is formed at the center of curvature of this, you can just reverse its orientation, right?
Yeah.
And after that, put your this final image should be either at the focus of the eyepiece, or focus should be here so that you can see it at near point, right?
Yeah.
Final two, final thing is same. Like, only thing is that you put an extra converging lens here. But the problem with this is that the total tube length becomes very large, right?
Yeah.
It is almost like this for far point vision, right?
Yeah.
Tube length is 4 times f1, like long telescope it will become, right?
Yeah.
So that's why it is not used so much. We have another alternative, which is Galilean telescope, which uses a slightly different principle. It uses a concave lens as an eyepiece. So you have rays that are coming normally, and they want to make an image somewhere here at the focal length, right?
Yeah.
AB, this is supposed to be your AB, right?
Yeah.
Then you put a concave lens in the middle here, right? So
Yeah.
real rays which are coming like this and trying to form an image here, now this is at FE. So this acts as a virtual object sort of, right?
Yeah.
And this is at FE, so final image should be at infinity here, right?
Yeah.
Infinity. So basically think of it as, first the body's image should come here, find that position, and then according to the difference here, you can find, you have to put the concave lens in such a way that this difference is FE, right?
Yeah.
Then these rays will actually not reach here and they will diverge, and finally image will be at infinity here. So this is the object for the concave lens, right? So basically keep this in mind. This is your FO, this is your FE. This is the arrangement, right?
Yeah.
After that, final image is at infinity. And you can see it from this side, and notice that it will be erect. It will be vertically upright because it's a virtual image now, right?
Yeah.
You can check it by calculations also. Do the calculation for, I mean, you already know image is here. Now just do lens formula here. 1 by V minus 1 by U is equal to 1 by FE, right? Now your 1 by V we have to find, and minus 1 by U is now positive here, right?
Yeah.
Positive FE, right? No, positive, correct. Yeah. And I should have gotten 0. I'm making a sign mistake somewhere. This is your object now. It is this side. I should have gotten V as infinity. No? What is the sign mistake that is happening? 1 by V. This formula is correct. No, lens formula we're writing correctly, right? Yeah, yeah. Wait, FE is negative for the lens, right?
Okay. Concave.
Concave lens, FE is negative, right?
Yeah.
Yeah, yeah. Then it will cancel, no, when you put the value.
Yeah.
Because here we have already accounted for the sign, no?
Yeah.
By putting it as positive. Let's say FE was 10 centimeters, right? When I take the first equation, when I write, I'll put 1 by this 10 as minus 10, right?
Yeah.
And for U, I will put, since it is 10 centimeter on the right side, it will be plus 10, right?
Yeah.
So it will be 1 by V minus 1 by 10 is equal to 1 minus 1 by 10. So now it is coming 0, right?
Yeah.
So V is at infinity here, right?
Yeah.
So this is a Galilean modification for the telescope. You get a erect image at infinity, but it is a virtual image, right? So there are normal telescope you need to understand properly, and then there are two modifications. The terrestrial telescope, where you put a lens in the middle, it adds an extra 2f1 plus 2f1 in the middle, right?
Yeah.
And the other one is the Galilean telescope, where you just use a concave lens before the focus of this, right? This is FO. And place it in such a way that this is FE, right?
Yeah.
Correct. Then the image will be this side, infinity. So these
Yeah.
are modifications that are done to ensure that your final image is upright, right? Now what you can do is practice a few problems. Like next class, we can do a few questions on telescopes and all, but mostly nothing more than this is required. Microscope, telescope, you just need to now apply it in 4 or 5 questions and you'll get the hang of it, right?
Yeah.
Practice a few questions. We can also do some problems if needed.
Okay.
Okay, that's all for now then.
Thank you.
Bye.